Hello and welcome to the fourth video in the normal distribution revision section. So we're going to look today at when we can use a normal distribution to approximate a binomial distribution. And this is a skill which sort of feels like, why do we need to do it? And I completely understand that question. There used to be a feature of the specification for A-level in the S2 module where we had to do these approximations, which is why it's still there, which is why it's in the specification. But the idea of approximating a binomial using a normal distribution it's useful. It's incredibly useful in two situations, and we need to know those two situations. So the two situations that you may be asked about, and in fact the reasons we can do this, are as follows. If n is large in a binomial distribution, so we've got a large number of trials, and p is close to 0.5, then a normal distribution can be used to approximate a binomial distribution. Now, when we say n is large, there's no definite definition of that. There's no, value of the number of trials beyond which it's fine. It's just a large number. And p close to 0.5, again, is fairly subjective, but we just have to say that it's as close to 0.5 as we can get it. And the idea here is that we are going to be approximating a real answer with an approximation. And basically what these two elements are telling us is that the larger the number of trials and the closer the probability of success is to a half, then the more accurate your approximation is going to be. Okay? So we've got two calculations that we need to know. All right, we're changing our number of trials and our probability of success into mu, which is the mean of the normal distribution, and sigma, the standard deviation. And we calculate these two things as follows. So mu is n multiplied by p. It's the expected value. Okay, so if we had an experiment where we conducted 20 trials and the probability of success was 1/4, you would expect that person to have 5 successes out of 20. Okay, that's the theoretical probability. 0.25 multiplied by 20 equals 5. So our mu is the number of trials times the probability. Now the standard deviation is slightly more difficult to work out. We don't need to prove this. You can prove this. We don't need to. And the fact that sigma is the square root of np brackets 1 minus p. So let's see how this works in real life. We have a biased coin with a probability of getting a head 0.53. The coin's tossed 100 times and the number of heads is recorded. So we can see that we've got two things going on here that satisfy the conditions to approximate. We've got a large number of trials, 100 trials, and we've got a probability close to 0.5. So the binomial model for x is as follows. So x distributed with a binomial distribution, number of trials is 100, and the probability of success is 0.53. And that's what part A of the question is asking. And it's always a good idea to write that down, even if you're not asked. Okay? Just makes things a lot clearer. So explain why we can use this approximation. We have a large number of trials. Okay? These are our two conditions. Now we have to state these, okay, to get marks, to get recognized, we have to state these two conditions. Large number of trials, we've got 100 here. And we've got a probability of success close to 0.5, okay, when in fact we've got 0.53. So those are our two conditions. And you get a mark for each condition. You must remember those two conditions and you must be able to use them. Find the values of mu and sigma in this approximation. So we have y distributed normally with mu and sigma squared, where mu is np, which is 100 multiplied by 0.53, which is 53. And then we have sigma squared, or sigma, which is the square root of np times 1 minus p, which is the square root of 53 np multiplied by 1 minus p, which is 1 minus 0.53, which is 0.47. And we'll do a little quick bit of calculus. So we've got 53 multiplied by 0.47, and then we take the square root of that. And we get 4.99. is approximately 5. So the distribution becomes n, the mu of 53, and sigma squared, 5 squared. So that means that we can now use this distribution to complete our calculations. Now that's the first thing that we've got to do. The second thing that we've got to do is think about the fact that the binomial distribution is a discrete distribution. That means that there's a whole number of trials only and a whole number of successes or fails. But the normal distribution is continuous, as we discussed in one of my previous videos. So the binomial random variable here, which I've written out, is approximated using the normal random variable here. So we're given that information in this question, which is interesting. 6.12 squared. Use the approximation to find this, the probability that x is less than or equal to 70. Now what I'm going to do here is I'm going to write a number line, as I always do, just to make sure that I'm using the correct values in my test statistic, as my test statistic. So less than or equal to 70, let's think about the numbers around about 70. 68, 69, 70, 71, 72. So it's just a little number line to help me work out what it is I'm interested in. So I'm interested in less than or equal to 70, okay? X less than or equal to 70. That's every number up to and including 70. Now the normal distribution, I should say first, the binomial distribution, nothing exists between 70 and 71, right? No numbers. There's a jump between 70 and 71 with nothing in between, a discrete jump, discrete random variable. However, with the normal distribution, there is, all right? There are an infinite number of decimals between 70 and 71, and so we need to take into account every single one of those decimals, which can be rounded to 70. And that means we're looking at the upper bound of 70. So over on this side, my y is actually less than 70.5. Now that's called continuity correction. We take our discrete test statistic and we check which of the upper or lower bounds we're going to use. And if you use this method of writing out the number line every time, you will never get it wrong. Less than or equal to 70 for a binomial means we have to be less than 70.5 for a normal, okay? Because anything 70.43 will round to 70 and therefore be included in the binomial distribution. So we're actually calculating the probability that y is less than 70.5. So straight to the calculator. And we're going to go to menu 7 for the class whiz, and if you've got the CG50, you go to your menu 2, and then you select your option F5 for your distribution, and then you follow those instructions from there on. So the probability that y is less than 70.5. We've got normal CD is what we're interested in. Our lower, if you remember, is our very small number, minus 100,000 will do nicely. Our upper is 70.5. Our sigma value is 6.12 given to us in the question. However, we could have calculated this. And our mu is 72. And our probability here is 0.4032. Okay, and that's our approximation. Now, just out of interest, okay, we can actually do this on our calculators. We can work out, we're not asked to work out, but let's work out the probability that x is less than or equal to 70 using a binomial distribution just to see how close we are. So we go to menu 7, and we'll go to binomial CD. We'll go to variable rather than list. Our x is 70, our n is 150, and our probability is 0.48. And we get 0.4036. So you can see that this approximation is fairly close, right? It's actually the same value to 2 decimal places. It's only at the 3rd decimal place where things change. So it's very similar. And you can imagine if the number of trials increased and the probability got slightly closer to 0.5, then this accuracy would improve. So let's have a look at B, and we're going to do exactly the same thing again. We're going to go the probability that x is greater than or equal to 80, but less than 90. So I'm going to do a number line here, maybe a couple of number lines, and we're going to have a look and see which numbers we're interested in. So in fact, let's just do it right up to 90. 79, 80, 81, 82, 83, 84. I'm going to run out of space. 85, 86, 87. Let's move all that along a little bit. Don't know why I wrote the whole number line out, but hey, it's going to be worth it. 88, 89, 90, 91. So we're looking at greater than or equal to 80, but less than 90. So greater than or equal to 80 includes 80, but less than 90 stops short. Okay, so here's my x, greater than or equal to 80, but less than 90, right? There it is. So now we're going to like turn this into something for our normal distribution. Okay, so greater than or equal to 80 means that we have to include 80, which means we're going to start here at 79.5 because 79.56 rounds to 80, so it needs to be included. And then we're going to go all the way up to here, and so for less than 90, we're going to stop at 89 for our binomial distribution. Okay, so it's got to be less than or equal to 89 here. But that means that we can include anything which rounds down to 89. Okay, so our y is going to be greater than or equal to 79.5, but less than 89.5. All right, because anything that's 89.5, so 89.43, for example, rounds to 89 and is therefore included. And anything 79.5 and above, so 79.5 itself, rounds to 80, so therefore will be included. So the probability that we're actually dealing with here is 79.5 right up to 89.5. Now, in case you're wondering about the less than or equal to, the less than, or greater than or equal to, or anything like that, obviously in the binomial distribution, whether it's less than or equal to, or greater than or equal to, whether it's greater than or equal to, or greater than makes a difference because actually there's nothing in between these two decimals. Okay, but with the normal distribution, actually it doesn't make any difference, as we said a couple of videos ago. All right, I'm just using the correct terminology because this is what would happen mathematically. However, you won't be marked down if you accidentally forget to put the or equal to. Okay, so let's go ahead back to menu 7 for our normal CD. So with our normal CD this time, our lower bound is 79.5 and our upper bound is 89.5. Our sigma is still 6.12 and our mu is still 72 because we're using the normal approximation, and we have 0.1081 4 decimal places. And that's it. Okay, that's it. Now, if I was to check the binomial distribution for this one, it takes slightly longer because we'll have to do some taking away. But if we go to binomial CD, and I'll just get the value so that I can check it as I'm talking to you. We've got x so greater than or equal to 80, 79 and take it from 1. So we'll store that in A. So 0.8898. And we're going to do less than or equal to 89 as well. And I can tell you that this comes out to exactly 0.1081. Okay? So we've got a very good approximation on our hands here. So that's continuity correction, okay? There's two things here that you've got to learn about approximating a binomial with a normal. One is that you can do it when n is large and p is close to 0.5. The second is that you need to know these two calculations. Mu is np and sigma is the square root of np1 minus p. Learn those, memorize those, practice those, okay? Because that's how you turn this binomial distribution into a normal distribution. Secondly is continuity correction. Now, we didn't have to calculate our mu and sigma here, but obviously we could have. We could have said that mu is np, which is 150 times 0.48, which is 72. Okay, it was just given to us in the question. And sigma, we could have worked out was np times 1 minus p, so 0.2 in there. And I'm just doing this to show you that we can do it. So we got 6.12, right? That's where those two numbers came from, the previous calculation, right? So 72, 6.12. So then we needed to use continuity correction, and I really do strongly recommend that you write out the number line, a couple of numbers either side of the value that you're interested in, mark on there what you would be calculating if you were using a binomial, and then use your upper and lower bounds as required to do the continuity correction. And that's it. So, happy approximating. I'll see you in the next video, which will be the last video, where we'll do some hypothesis testing. Okay, thanks everybody.